Hello, and welcome to Why is Math Like That? The show in which we take some puzzling fact about math and attempt to explain why it is the way it is. I'm your host, Tony, and you're watching the channel Tony Talks About Math. In this episode of Why is Math Like That, we're exploring a funny technical detail about writing numbers as decimals, which for some reason stirs up rather strong feelings for some people. I have heard people argue passionately and at length that this fact should not be true, and yet it is. The technical detail I'm referring to is the fact that 0.99999 repeating and 1 are two different ways of writing down the exact same number. Why is that? Or more succinctly, why does 0.9 repeating equal 1? The first thing we should clarify here is that there's a difference between a number and the way we write that number down. When we write a number, we're trying to give it a name that clearly identifies it, and there can be more than one way of doing that. This is something that we're very used to in a lot of different contexts. Stepping away from numbers for a moment, we don't have a hard time accepting that the identifying phrases, the lady with the lamp, the first woman elected to the Royal Statistical Society, the founder of modern nursing, and Florence Nightingale all indicate the same person. When it comes to numbers, we recognize that the fractions 4 over 8, 3 over 6, 2 over 4, and 1 over 2 all identify the same number, which is found on the number line in the very middle of the interval that stretches from 0 to 1. We cheerfully accept that this same number can be written as a fraction infinitely many different ways. Some of those ways correspond rather neatly to certain decimal representations. For example, if we write 5 over 10, we can match that up with the decimal representation 0.5, 5/10. Since there's only one digit to the right of the dot, we know that this decimal represents a fraction with denominator 10. Similarly, 50 over 100 corresponds rather nicely to 0.50. Since there are two digits to the right of the decimal point, this represents a fraction with denominator 100. And we can go on and on like this, thousandths, 10,000ths, etc. We're even pretty comfortable with a decimal expression that can't be tied in the same way to a specific numerator and denominator. I'm talking about an infinite decimal. If we write 0.500000 with the digit 0 repeating forever, we're not specifically talking now about tenths or hundredths or thousandths or millionths or any of those. It's not clear what numerator and denominator are indicated by this decimal expression. However, we still see this as the number 1/2, and all those extra zeros don't bother us. They're just 0 anyway, so we don't mind them. On the other hand, if I go on to claim that another decimal representation of the same number is 0.49999 with the digit 9 repeating forever, then I think people are going to start to ask questions. Now, saying that 0.4999 repeating equals 1/2 is basically the same as saying that 0.9999 repeating equals 1. This video is about 1, not about 1/2. Over the next few minutes, I'm going to present you with about 6 different explanations for why 0.9 repeating really represents the same number as 1. The first few explanations are basically tricks using arithmetic or basic algebra, and we'll look at them and talk about why they might or might not be convincing. Some people like them, some people don't. Then we'll get a little more formal, and I'll give you a couple of explanations that might feel familiar to those of you who've studied calculus. If you're terribly averse to mathematical rigor, you can just sort of hum through that part. It won't last long. If instead you're drawn to mathematical rigor and you want to see those details, you might want to hit pause at certain points, because much like life, that part goes by pretty fast. Finally, I'm going to show you some pictures and animations that I think illustrate and aid certain intuitions for why 0.9 repeating really is just another way of writing the number 1. As a way of warming up for the arithmetical tricks that we're going to start with, let's go ahead and take a look at this rather alarming representation of the number 1/2. Okay, so if this number, 0.4999 repeating, really equals 1/2, then we should be able to multiply it by 2 and get the answer 1. Now, this immediately presents us with a problem, because usually when we multiply numbers this way, we start at the right, and there is no right end of the number 0.4999 repeating. We can multiply going from left to right, especially since we're only multiplying by 2, but to make it even more approachable, let's, instead of saying we're multiplying by 2, say that we're just adding this number to itself. And now we'll proceed with this addition, left to right, and we'll be careful. So, of course, 0 plus 0 is 0, and 4 plus 4 is 8, but before we really commit to that 8, we've got to think about what's in the next column. Are we going to be carrying a 1 from the next column to the left? Since those are 9s in the next column, and 9 is a big number, 9 plus 9 is more than 10, we will be carrying a 1, so that 8 should really be a 9. Okay, super. Let's move to the next column. 9 plus 9 is 18. The 1 we've already dealt with, and then that 8 is not really an 8, because in the next column there's a pair of 9s, so there's going to be a carried 1, and we're going to have another 9. And this same thing is now going to happen in every spot. 9 plus 9 is 18, but the 8 from 18 becomes a 9 when you carry a 1, and we have a 9 and a 9 and a 9, and it's all 9s. So we added 0.4999 repeating to itself, and we got 0.9999 repeating, which might equal 1. Interestingly, that's the same thing that we would have got if we had just added 0.5 in the first place. Isn't that intriguing? Well, I think it's safe to say that we have warmed up and we are fully into arithmetical tricks now. So let's change the title on the screen and see what the next trick is going to look like. This next trick is a bit like the one we just saw, but it uses an infinite decimal that's a bit more approachable, namely 0.333333 repeating, known to users of calculators the world over as 1/3. Now, if we take another 0.3 repeating, which is to say another 1/3, and we add these together, well, this is a nicer addition than the last one, because there are no carry digits to worry about. In every column to the right of the dot, we just have 3 plus 3 equals 6, so we get 0.66666666 repeating. Or, adding the fractions, we have 1/3 plus 1/3 equals 2/3. And we also recognize this one, 0.6 repeating equals 2/3, and that's great. Now let's add another 0.3 repeating to that, which is to say, let's add another 1/3 to our 2/3. Again, no carry digits to worry about. In every column, we just have 6 plus 3 equals 9, so we get 0.9 repeating, which is 2/3 plus 1/3, or 3/3, and that equals 1. What do you think? Is it convincing? Does it feel like something tricky is happening here? Well, if you don't like the fraction 1/3, perhaps you prefer 1/9. As a decimal, 1/9 is 0.111111 repeating. And now if we take a bunch of these, let's say 9 of them, and add them all up, Then in every column, we're going to add 9 ones together, and that'll give us a 9. So we get our 0.9 repeating, and that's 9/9, which again equals 1. Oh, what's that? You're not a big fan of ninths? Well, let's try 11ths. You probably like those more. 1/11 is 0.090909, etc. And if we take a bunch of those, let's say 11 of them, and add them up, we should get 11/11ths. But this one's a little trickier because how exactly are we doing this addition? Well, I think it's easiest to see if you take the columns to the right of the decimal point and pair them off. So if you look at every 2 columns, you have 0/9, which is to say 9, repeated 11 times. And 11 nines makes 99. So when you add these up, in every pair of columns, you get a 99, and that means we get 0.999999, which is 0.9 repeating, as our decimal for 11/11ths, which again equals 1. I think it's fair to say at this point that these examples are getting worse, not better. I mean, if this last one is good for anything, it might be that it helps you remember the decimal for 1/11th. Indeed, we could make more and more of these, and they would just get more and more arduous. Let's not do that. If you feel that there's some sort of sleight of hand going on here, I don't entirely blame you, and I'm going to say something about that. But first, let's look at one more arithmetical trick that's a bit different from these. This next trick works like this. Let's think about taking the average of 2 numbers. Suppose you want to average 2 numbers, we'll just call them A and B. Then remember the trick for doing this, right? We're going to add the 2 numbers, A plus B, and then divide that sum by 2, and we get the average. So for example, just quick review, if A is the number 4 and B is the number 6, then we add 4 plus 6 and divide by 2, so that's 10 divided by 2, which is 5, and that's good. 5 is the average of 4 and 6, or another way of saying it, it's the number on the interval between 4 and 6 that's right in the middle. Okay, great. So what if you do this? You average 2 numbers, A plus B divided by 2, and the answer you get is one of the 2 numbers. What if it's B? Well then, what does that mean about the 2 numbers? We can see this a couple different ways. If we do just a little bit of algebra, we can see something. Let's take this equation, A plus B over 2 equals B, and multiply both sides by 2. Then we get A plus B equals 2B. And then if we subtract a b from both sides, we get a equals b. So it looks like if you average 2 numbers together and you just get one of the 2 numbers, then those must have been the same number. Even without that algebra, this might be easier to see geometrically. If you say that you're going to take the interval from a to b, and the point right in the middle of the interval is also b, then I guess it's also a, because there's no distance between the 2 points. When you go right in between them, you're still at one of them, so they're all in the same place. Okay, great. So let's now see our trick. We're going to do this average thing with our A being the number 1 and our B being the number 0.99999 repeating. So first, we're going to add them together, and we'll write 1 with all the zeros after it, just so we have all the columns to add. And then we write 0.9 repeating under that, and we write our plus sign. And this is a nice addition because you're just adding 0 to other things. So of course we get 1.99999 repeating. Now we want to take this number and divide it by 2. And here's where you see the advantage of this trick over some of the others, because when we divide via long division, so let's set up our long division, we actually start at the left, not the right. So this feels a little more natural. Now, if we're going to do this long division, okay, let's see, 2 into 1. Well, 2 doesn't go into 1, so we put a 0 first. And then the 1 and the 9 make a 19, so 2 goes into 19 9 times. 9 times 2 is actually 18, and then we subtract and we get a 1, and I'm just have the decimal point there along for the ride. Now we bring down the other digits, and the first two digits we're looking at are again a 19. 2 goes into 19 9 times. 9 times 2 is 18. We subtract, not worried about the decimal point anymore, and we bring down the other digits. And now you can see this is just going to keep going the same way. We're going to keep getting a 1 with a bunch of 9s after it, after every subtraction. And so we get all 9s as the result of the division. Well, we averaged the numbers 1 and 0.9 repeating, and right in between them we found 0.9 repeating. Well, that tells us that this interval, stretching from 0.9 repeating to 1, is really just a dot, and 0.9 repeating and 1 were the same thing all along. Okay, so that's the last of the arithmetical tricks that I'm going to show you, and you might find some of these convincing, you might like these, you might feel like I'm pulling a fast one on you. If you feel that way, I'm just going to pull one more fast one on you, but this one will involve algebra. So, as is traditional in algebra, let us start by taking the thing that we want to know something about and calling it x. Oh joy. Now, if we can talk about x, perhaps we can also talk about 10 times x. Multiplication by 10 is very nice, of course, because we're working in base 10. So if x is 0.99999 repeating, then 10x must be 9.99999 repeating. Just move the decimal point over. Now, there are a couple different ways to get through this argument. One way would be to say that the number we've just written down is also 9 plus x, so 10x equals 9 plus x, and then solve that equation. I'm going to do something equivalent, which is to just write the original x under the 10x and do a subtraction. So on the left, we say 10x minus 1x is 9x, of course. And on the right, where we have all these decimals to subtract, we notice that to the right of the decimal point, all the 9s match. 9 minus 9 is 0, so the answer we're going to get is 9.0000000 forever. Or, as we usually call it, 9. So 9x equals 9, and that pretty quickly implies, by dividing both sides of the equation by 9, that x equals 1, just like it has every other time. Haha. Now, why am I calling all of these arguments tricks, and why do I keep suggesting that there's something sneaky going on? Well, there is something sneaky going on here, and it's this. We're using rules of algebra and arithmetic that we're used to, but we're used to applying those rules to numbers that just have a few digits. We are very comfortable adding, subtracting, multiplying, dividing, 1-digit numbers, 2-digit numbers, 5-digit numbers. I think we believe that these rules will work with a 20-digit number with 10 digits to the left of the decimal and 10 digits to the right. But in all of these examples, we've just been blithely assuming that what works for a number with a finite number of digits will also work for a number with infinitely many digits. In doing this, we've just been sweeping infinity under the rug and acting like it's not somehow in the room. So if this feels a little bit tricky, that might be why. We haven't really confronted the ... that is written at the right end of most of our numbers here. The next thing we're going to do is actually confront that ... and go ahead and look at the infinity that's involved somehow. And we're going to do that by turning the question around first, and by saying, well, what if 0.9 repeating isn't 1? What if they're different numbers? Then what is the difference? Now, when we ask what's the difference between two numbers, remember that the word difference has kind of a formal meaning in mathematics. You can think of it as the distance between the two numbers on the number line, but more concretely, it's what do you get when you subtract the two numbers? What is 1 minus 0.9 repeating? Now, I've written the subtraction in this order because we want to subtract the smaller number from the larger number to see a positive difference, and if one of these numbers is larger, it must be 1. After all, look at the digit just before the decimal point. I realize I didn't write a decimal point next to the 1, but you know where it goes. The number 1 has a 1 just before the dot, and the number 0.9 repeating has a 0 just before the dot. So if one of them is bigger, it must be 1. Anyway, what do you get when you subtract them? We don't know, but we do know this, just because of how subtraction works. If you take that difference and subtract it from 1, you should get 0.9 repeating again. So let's use that to think about how small that difference must be. First of all, it's less than 1/10. Why is that? Well, if you take 1 and subtract 0.1, which is 1/10, from it, you get 0.9, and there we've gone too far. We've got 0.9, which is smaller than 0.9 repeating, so we subtracted too much from 1. For a very similar reason, this difference must be less than 1/100th, which is 0.01, because if you subtract that from 1, you get 0.99, and again, that's too small. We've subtracted too much. Now, we can keep doing this, so what can we conclude? The difference between 0.9 repeating and 1 must be less than any positive number, no matter how small. Why is that true? Because no matter how small a positive number is, one of these numbers, 1/10th, 100th, 1/1000th, 1/1,000,000th, 1/1,000,000,000th, is eventually going to be smaller. So let's make this a little more formal. The difference, 1 minus 0.9 repeating, is less than 1/10th, and it's less than 1/100th, and it's less than 1/1000th. And just to not have to write down a bunch of zeros, I'm going to start using exponents. It's less than 1/10 to the 4th power. It's less than 1/10 to the 5th power. In fact, it's less than 1/10 to the nth power for any n, even as we let n get bigger and bigger and bigger and approach infinity. And there it is. We're no longer sweeping infinity under the rug. We're looking directly at it, and we're practically doing calculus. Now, at this point, if you agree that something that's smaller than all the positive numbers and yet isn't negative, then it's 0, then we're done. Number smaller than all the positive numbers, but not a negative number. Where else can you go? It must be 0. If you think there's some wiggle room there, you might be interested in a funny area of math called non-standard analysis, where mathematicians talk about numbers called infinitesimal numbers that are smaller than all the positive real numbers. They're infinitely small, and yet they're not negative and they're not 0. They're infinitely small numbers that you can somehow work with, and by working with them, you have an alternative way of formulating the foundation of calculus. So that's fun and all, and I've seen the argument made that by using a construction called the hyperreal numbers, which is part of non-standard analysis, we can get 0.9 repeating to actually be different from 1. Trouble is that doesn't work, because the expression 0.9 repeating, when you're working with hyperreal numbers, doesn't actually mean anything, because within the hyperreals, there's not a unique number that's bigger than 0.9, bigger than 0.99, bigger than 0.999, bigger than all of those, and yet smaller than 1. There are infinitely many numbers in that space, and no one of them is the smallest. No one of them has the claim to be 0.9 repeating. So people doing non-standard analysis just don't write down expressions like 0.9 repeating, and that's not what's going to save us. If we write down 0.9 repeating, then we're using standard calculus, and I guess we've arrived at the point where we're going to look at the standard mathematical proof of why 0.9 repeating equals 1. Now, you might say that this whole video, indeed the whole channel, is pretty mathy, but nevertheless, heads up, it's about to get real mathy in here. I'm going to go through a proof here, I'm going to use a formula, then I'm going to prove the formula, and by the end it's really going to smell like calculus. Anyway, you've been notified, let's go. We want to talk about the number 0.9 repeating, so first let's unpack what that even means. Right at the end of this video, I'll give you an alternative way of thinking about what an infinite decimal means, but for now we'll go with the standard. The first digit is 9/10, and then you add 9 100ths for the next digit, and then 9 1,000ths for the next digit, etc. So an infinite decimal is really an infinite sum. Now, infinite sums can be tricky to evaluate or even to figure out whether they equal anything at all, but in this case we're lucky because this infinite sum is what we call a geometric series, and that kind is pretty straightforward to work with. In order to know everything about a geometric series, we just need to know what's the first term. Well, let's look. It's 9/10. We'll call that A because that's what we usually call it. And then we also need to know, what do you multiply each term by to get the next term? Well, notice that you can take each term and multiply by 1/10, multiply by 1/10, multiply by 1/10, and you can keep producing more terms that way. The fact that it's the same multiplier at every step is what makes this a geometric series, and that number that we multiply at every step is a constant ratio between terms. We call it R. Once we know A and R, we can apply the famous geometric series sum formula. That says that if you have A plus A times R plus A times R times R plus A times R times R times R, etc., then it will equal something if and only if the number R is small. And by small, I mean its absolute value is smaller than 1. In this case, it's positive, so we're not worried about the absolute value, and 1/10 is definitely smaller than 1. That's what makes each term smaller than the previous term. Anyway, when that happens, the series equals the value A divided by 1 minus R. Great. How does that work in this case? Well, we want to plug into A divided by 1 minus R, and we figured out that A is 9/10 and R is 1/10, so let's just throw those numbers into the formula. The denominator, 1 minus 1/10, is 9/10, and so we have 9/10 divided by 9/10, and any number divided by itself equals 1. Super. Well, we've shown now that 0.9 repeating equals 1 if you believe the geometric series sum formula here. So, in case there's any question about that, let me run through that proof. So, we have A plus A times R plus A times R squared plus A times R cubed plus dot dot dot. First thing we're going to do is recognize what it means to have a dot 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 at the end. It means that we're going to consider taking this sum as far as A times R to the n, and then letting n get bigger and bigger. Formally, we write it this way. Limit as n goes to infinity of this finite sum. Now, we can factor an A out of both the sum and the limit using the distributive rule and a nice limit rule from calculus. Next, we rewrite the somewhat clunky expression in parentheses using some algebra, so it looks like this. If you're not sure that those two expressions are equal, try multiplying both of them by 1 minus R and see what happens. Anyway, when you look at the fraction that we're taking a limit of, you notice that only one of the terms has anything to do with n. All the others are just either 1 or R. R. So let's move the limit up to the place where it matters. And now we wave our calculus wand and say that this limit equals 0. This is the part that depends on R being a small number. If I wanted to make this video longer and a little bit more rigorous, I would also prove that this limit really equals 0, but I'm going to skip that for now. If you want to ask about it in the comments, let's talk about it there. Maybe we'll talk about this in another video. Anyway, now we're basically there, because the numerator 1 minus 0, that's just 1. And now we can multiply the a back into the fraction, and we get our formula, a divided by 1 minus r. So now you've seen where the geometric series sum formula comes from, and we have our proof that 0.9 repeating equals 1. Now what I've found from experience is that this argument, this proof, is the most persuasive when you present it to people who have studied formal mathematics. So mathematicians, college math majors, etc. If you ask them, why do you believe that 0.9 repeating equals 1, they will often talk about this proof. People who haven't studied more formal mathematics, I find, are less likely to be convinced by this one and might be happier with one of the arithmetical tricks we looked at earlier. I'm now going to show you something different from either this or the arithmetical tricks, because we're going to look at some fun pictures with moving parts. And if you don't find anything convincing so far, you might like something that you see there. The first picture we're going to look at is an illustration of how the number 1 and this sum here, 9/10 plus 9/100 plus etc., really do represent the same amount. So here's a rectangle, and we're going to say that the area of this rectangle equals exactly 1. Now, if we take this rectangle and divide it into 10 pieces, then each of those pieces, since they're all equal, has area 1/10. And if we fill in 9 of them, then we've shaded 9/10 of area, which is 0.9. We can take that remaining 10th and divide it into 10 pieces. Each of those is 1/10 of 1/10, so it's 1/100th of the original rectangle. And if we fill in 9 of those, that's 9/100ths. We can take that last 100th, divide it into 10 pieces. Each is 1/1000th of the original rectangle, and we can fill in 9 of those. There's 9/1000ths. That's the next 9 in the decimal expansion. We can keep going and fill in 9/10ths of that last 1,000th, leaving only 1/10,000th up in the corner. And we can fill in 9/10ths of that. And at this point, it's hard to see that there's any area that isn't filled in. However, we can zoom in here and see, indeed, there's some white area in the corner that we haven't covered yet. However, you can also see that if we keep doing this, there is not a white pixel inside this rectangle that won't eventually be covered. We might just take a while to work our way that far into the corner. If 0.9 repeating were less than 1, then there would have to be some white area that we never ever reach. And yet, no matter what spot you pick in the white, it will eventually be reached by one of these shaded areas. So that is a visual proof that 0.9 repeating equals 1. Now the next picture I want to show you is a little bit different because it's going to give you a different way of thinking about what these infinite decimals even mean. Here we have a stretch of the number line reaching from about 0 to 3. And we're going to step away from 1 for a moment and focus on a different number. I've chosen an irrational number, and I thought about using pi, but pi is a little bit overplayed, so I'm going with a slightly less famous phi, which you may have heard of. It's also known as the golden mean. And we're going to look at the decimal expansion of phi as a set of directions for finding where it is on the number line. So what is phi anyway? Well, it starts out as 1 point something. And that right away tells us that we're going to find it somewhere in this interval between 1 and 2. It's not less than 1, it's not bigger than 2. Now, we can zoom in on this interval and note that it is divided into tenths from 1.0 up to 2.0. And by looking at the next digit of phi, which turns out to be a 6, we know which of these intervals to look inside of. It's the one between 1.6 and 1.7. That's where we're going to find our number. So let's zoom in on that interval and see that it has subdivisions, 1/100th in length. And if we see that the next digit of phi is a 1, then we know we want to look between 1.61 and 1.62 to find it. Each digit gives us a more precise set of directions for finding where should we look to find this number. So we zoom in between 1.61 and 1.62, and we look at the subdivisions there. Now, should the next digit happen to be a 0, we would want to look at the box all the way on the left. Should the next digit happen to be a 9, we would want to look at the box all the way on the right. As it happens, the next digit of phi is an 8, and so that tells us we should look in the box second from the right. And so on. We can keep doing this forever. The reason we can keep picking one interval at each step is because phi, an irrational number, happens to not match up with any of the hash marks that are separating these intervals on the number line. It's not exactly 1.618, it's not exactly 1.619, it's somewhere in between. The number we're interested in this video is 1, which is one of the hash marks that we've made. So let's back this process up and focus on the number 1. So let's put the number 1 in the middle of the screen and think about how we're going to do this. Now we're locating a number by choosing intervals, but 1 is a hash mark that separates two intervals. So it kind of has equal claim to be part of the interval from 0 to 1, or to be part of the interval from 1 to 2. Those both seem like valid options. So if we choose the interval from 1 to 2, then the number 1 is going to start with 1.0 because of all the subintervals between 1 and 2. It belongs to the one all the way to the left. On the other hand, if we're going to choose the interval between 0 and 1, then the number 1 is going to start 0.9 because it belongs with the interval all the way on the right. It certainly doesn't go with any of the others. Now, if we want to get more precise, which is the idea of going through more decimal places, then if we're on the right, we'll say that the next digit is also a 0 because of all the intervals between 1.0 and 1.1. 1 clearly belongs to the one on the left between 1.00 and 1.01. On the other hand, if we're going with the 0.9 expression, then the number 1 belongs to the interval all the way on the right, the one between 0.99 and 1.00. We can keep doing this and see that if we want to zoom in on the number 1, we can either do it from the right or from the left. There's really no difference between the two options. It's a lot like this situation. Suppose you want to give someone directions from one corner of a city block to the opposite corner. Well, there are two perfectly good ways of doing this. You can say, start by going left, and then after that, when you get a choice, keep right. Or you can say, start by going right, and then when you get a choice, keep left. Either one will get you to the opposite corner. In terms of the number 1, we can write 0 point to say start by going left, and then all of those 9s say after that keep right. Or we can say start by going right and write 1 point, and then say after that head left with a bunch of zeros. Either way, we've given directions to the same place, and it's a very symmetric situation. There's no reason to prefer one over the other. And that's all I have to show you for now. Thank you so much for watching this episode of Why is Math Like That? I hope that you've found this entertaining and in some way thought-provoking. If you started this video skeptical and dubious of the idea that 0.99999 repeating and 1 were somehow two different ways of giving directions to the same place on the number line, what do you think now? Are you convinced? If you are convinced, whether that happened in the last few minutes or long ago, which of the arguments that you've seen here do you find the most persuasive and why? Again, let me know in the comments. I'm really curious what people have to say. Anyway, thanks again for watching, and I look forward to seeing you on the next episode of Why is Math Like That?